So chemistry, we're moving into the last lesson of this short unit on gas laws, and it's going to just add some more facts about gas laws. So we're going to start off with a little bit of a side topic that you're going to use throughout the rest of this course, and it's on unit cancellation when they're a little bit complex. Sometimes they can get that way, and so you're going to see how to deal with those. So as we move further into this course, unit of measure cancellation will become more complicated. Use the principles of fraction division to cancel units. So if two levels of the fraction have a word in common, then the units on those levels can be canceled. So let's look at this down below. You have a fraction, and then on the top of the fraction you have another fraction. On the bottom you have another fraction. So the fraction on top can be called the numerator fraction, and the fraction on the bottom can be called the denominator fraction. So because it would be confusing maybe to call the top of the numerator fraction the numerator, we're going to call it the numerator top. And the bottom of the numerator fraction we'll call the numerator bottom. And then if you go to the bottom fraction, we have the denominator top and the denominator bottom. So it's a fraction over a fraction. So what happens if you have units in this kind of complicated fraction situation? So let's take an example. And this is kind of a puzzle. You're not going to see anything in actual chemistry this complicated, but it's kind of a way to play with this concept and learn how to cancel units properly. So there you see we have a lot of units. I just kind of put them together randomly. So on the top of the numerator, on the numerator top, you have Kelvin for temperature, atmosphere for pressure, and liters for volume. On the numerator bottom, you have Kelvin again, you have moles, and you have grams. Then you go to the denominator fraction, and you have grams, atmospheres, and liters. And on the bottom of the denominator bottom, you have liters, moles, and grams. So how would we cancel those units following these rules? So again, if any of the two words, either numerator is in common, bottom is in common, top is in common, or denominator is in common, then you can cancel the units. So let's take the first one, and you can go in any order, by the way, and you'll get to the same result. So here we started with Kelvin there. So you have Kelvin in the numerator top and you have Kelvin in the numerator bottom. Since they both have the word numerator in common, they can cancel. Next we go to atmospheres. You have atmospheres in numerator top and in denominator top. So since they both have the word top in common, they can cancel. Next we go to liters. We have liters in several locations, but we chose the one in numerator top and denominator top. Since they both have the word top in common, they can cancel. Next we have grams. And we have grams down in the denominator top and also in the denominator bottom. Since they both have the word denominator in common, they can cancel. And moles. We have moles in numerator bottom and in denominator bottom. Since they both have the word bottom in common, they can cancel. So that leaves us with only two units that didn't cancel, the grams and the liters. So the way you would write that is, since all the units in the numerator top have been canceled, then you put a 1 up there. And since all the units in the denominator top have been canceled, you put a 1 there. So it looks like this. 1 over G over 1 over L. And the rules for dividing two fractions, we talked about this on the very first day of class, is you flip the bottom and multiply. So the 1 over L becomes L over 1, like this. And then you just multiply and you get L over G. So that seemed a little tricky, but and you won't you won't experience any of this complicated in a real problem, but it teaches you the rules. Okay, so let's move on, continue with gas laws. So standard temperature and pressure is a temperature of 0 degrees centigrade or 273 Kelvin and 1 atmosphere of pressure. Now 1 atmosphere's pressure is very normal. We talked about that. That's the pressure at sea level. That's the air pressure at sea level. 0 degrees centigrade might sound a little bit cold. It's the freezing point of water. But for most gases, such as H2, O2, N2, and they freeze at hundreds of degrees or very, very many degrees below zero on the centigrade scale. So for a gas, 0 degrees centigrade, 273 Kelvin is not really all that cold. So using STP, standard temperature pressure, and the ideal gas law, we can determine the relationship between the number of moles and the volume of a gas. So we can determine that 1 mole of a gas is equal to 22.4 liters. How do we do that? Well, here's the ideal gas law. It's PV equals nRT. And what we're going to do is solve for V. So you just do one algebra step to do that. You divide both sides by P. The P cancels on the left, and the V is left alone on the left side. And over on the right, you have nRT over P. So let's go ahead and plug in the different variables here. So N, number of moles. So we're trying to find the volume of 1 mole of gas. Notice it doesn't matter what the gas is. We don't state what the gas is. So this is true for any gas. So N, the number of moles, is 1 mole. And then you have the ideal gas constant, 0.0821 liter atmospheres over moles Kelvin. And then you have the temperature. Now the temperature has to be in Kelvin. Why? Because the ideal gas constant units are in kelvins. So you can't have the temperature in centigrade. And then down on the bottom we have the pressure, and it's 1 atmosphere. Again, the pressure has to be in atmospheres, not pascals or torrs or anything else. Why? Because again, look at the ideal gas constant here. It's liter atmospheres over moles Kelvin. That constant is telling you what units you need the pressure, temperature, and volume to be in. Okay? So now we have the numbers set up. Let's see if the units cancel. This is what the ideal gas constant does, is it sets up a bunch of conversion factors, so all the units cancel except the one we want, which is for volume, and that should be in liters. And you can see over on the right, the answer is 22.4 liters, but let's look at the unit cancellation. We cancel Kelvin and Kelvin, so Kelvin is in numerator top and numerator bottom. Moles is in numerator top and numerator bottom. Atmospheres is in numerator top and denominator top. Down on the bottom, there's only one level in the denominator, but that means it's on the top. So the only thing we have left is liters, and that's what our final answer is in. So what this means is that 1 mole of any gas, it could be H2, it could be helium, it could be CO2, it could be anything, at standard temperature pressure, is going to occupy 22.4 liters. Think about that. You all know what a 2-liter bottle of soda looks like. So imagine 11 of those, and then just a little bit more than that. And that's that. If you just opened all those bottles, 11 bottles plus a little bit more to the atmosphere, you would have 1 mole of air molecules, N2 and O2, in those bottles. So that's what you're saying. This means that 1 mole of any gas will equal 22.4 liters in volume, and now that has to be at standard temperature pressure. Okay, so let's do a stoichiometry problem with this. So let's look at this graphic organizer. It's just a little bit more complicated than the ones we've used before. Look in the bottom. Look at the chemical equation down. It looks exactly like the graphic organizers that we've used before for grams to moles and moles to grams calculations. What we've added here is a level on the top for liters of gas. So that would have to be gases up on the top in liters. And you notice that the moles to liters conversion are all the same because it doesn't matter what the gas is. It's always going to be 1 mole of any gas equals 22.4 liters. So now we can go ahead and introduce a problem. So how many grams of H2O will be produced from the combustion of 12.4 liters of CH4 at STP? Okay, so the question is how many grams of H2O will be produced from the combustion of 12.4 liters of CH4 at STP. So you notice that we have now 12 boxes to choose from, 12 open boxes. Down at the bottom, it's the same ones. It's grams at the very bottom. It's moles inside the chemical equation. And now we've added this top level for liters. Those have to be gases up there in the top. And you notice that the conversions, the molar conversions, are all the same, because it doesn't matter what the gas is. 1 mole of any gas will equal 22.4 liters, so all of those conversions are the same. So let's go ahead and start filling in the boxes, okay? We're starting with 12.4 liters of CH4, so where's that going to go? It's going to go up in the liters row, up at the very top, above CH4, so we're going to go ahead and put that there. And then where does our question mark go? How many grams of H2O? Well, you did this before in lesson 18 and 19. It goes down on the bottom row and underneath H2O. So there it is, way over there on the bottom right. Okay, so what's the path to get us from 12.4 to the question mark? So we've got to go down into the equation first, figure out the number of moles of CH4. Then we come across, figure out the number of moles of H2O, and then we come down using the molar mass conversion for water. 1 mole equals 18.02 grams to get our final answer in grams of water. So this is a 3 conversion problem. So we're going to go ahead and put the 12.4 liters CH4 way over on the left and some unknown number of grams of H2O on the right, where our final answer would be. And there's our first conversion. And it's simply 1 mole of CH4 for every 22.4 liters, or 22.4 liters for every 1 mole. So which of those is going to go in the first box? It's going to be this one. And you notice I'm not drawing boxes here. That's okay. So there it is. So you see that liters of CH4 is going to cancel with liters of CH4. And now we're sitting down in the moles of CH4 box down there right below the letter CH4. Okay, now next we have to go from CH4 to H2O. And what is that conversion factor? It is simply taken out of the equation. 1 mole of CH4 equals 2 moles of H2O. So we're going to go ahead and put those conversions up above. Right there. Okay, which one are you going to choose to go in that next location? Well, you have moles of CH4 on the top of the first conversion, and that needs to cancel out. So we're going to put this one up there, where moles of CH4 is on the bottom. So moles of CH4 cancels with moles of CH4. And now we're sitting in the moles of H2O box over there on the right, in the middle. So now we need to get out, and we need to get to grams of H2O. What's our equivalency for that? It's the molar mass. It's 1 mole of H2O equals 18.02 grams of H2O. So there are your 2 conversions up there. Which one of those 2 is going to be the last conversion? You need moles of H2O to cancel out and grams of H2O to appear on the top for the final answer. So it's going to be this one. So you go ahead and put that one there. Moles cancel with moles. And the units remaining, the last man standing, is grams of H2O. So now you multiply 12.4 times 1 times 2 times 18.02, everything on top, divided by everything on the bottom, divided by 22.4, divided by 1, divided by 1, and that gives you 20 grams of H2O. And there's no need to write it in the graphic organizer, but there it is down there on the bottom anyway. Okay, so it's done just the same as the stoichiometry you did before with grams to moles. Not the same as solution stoichiometry, but the same as the grams to mole stoichiometry we did in days 18 and 19. Okay, now we move on to discussing density. We talked about what density is. We've defined it before. It's the mass per unit volume. It's how much matter, how much mass you're cramming in to a certain amount of space. So gas density is the mass of the gas divided by the volume it occupies. So there's 1 hydrogen gas molecule in the volume to the right. When a second molecule is added, the density doubles. You have twice as much mass in the same amount of volume. You could also increase the density by it remaining as 1 molecule and then squeezing down the volume so it's a smaller volume. So you can change density by either adding or decreasing the mass, or adding or decreasing the volume that it occupies. So density can also be increased when the volume is decreased. So density is mass divided by volume, and it's m over v. Small d equals m over v. Sometimes density uses the Greek letter rho, which looks like kind of a scripted P. It's the Greek letter rho, but we're going to use D. It makes more sense. So the molar mass of a gas can be determined if the density is known, starting with PV equals nRT. I'm going to show you how to derive this equation. You don't need to do this on a test, but let me just show you. Start with this. Now you multiply by mass, okay? You can do that in math. It's legal as long as anything you do to the left side, you do the same thing to the right side, it's legal. So we're going to multiply both sides by mass. So you have now see that you have mass on both sides of that equation. Now we're going to divide both sides by moles N, volume V, and pressure P. It's a lot of things to divide at one time. And then we're going to group the M and the V together. So let's see what all that means. There it is. Okay, so we've divided both sides by the P and the V. So they're down on the bottom of the right side now. And we have also divided by the number of moles. So now it's down on the bottom of the left side. So now we have mass over number of moles. And we group the mass over volume over on the right side. Now what is mass over volume? That's density. So mass over number of moles is grams per mole, which is, maybe you didn't recognize it, that's molar mass, grams per mole. The weight for a certain divided by the number of moles. So M over V is mass per volume, which is density. So therefore this formula becomes molar mass, capital M is molar mass, equals density times R times T divided by P. So if you know the density of a gas and its temperature and pressure, you can compute its molar mass, and from that maybe you can determine what that gas is. So let's see an example. So MM is molar mass and density is measured in grams per liter. Okay, so Dalton's law of partial pressures. Actually, we're not going to see an example of what I just showed you. We're just going to move on to this. So Dalton's law of partial pressures uses the concept of mole fraction, which we learned back in the solutions lessons. So Dalton's law of partial pressure states that the pressure of a mixture of different gases in a container is the sum of the individual pressures of the gases. So the pressure of the total gas is P1 plus P2 plus P3. So if the gases occupy the same container at the same temperature, then the pressure is directly related to the number of moles. So there you have pressure of gas number 1 is equal to the number of moles of number 1 times the things in the parentheses all stay constant. The gas constant, the temperature, and the volume. Those are all going to be constants for all the gases involved here. So P2 would be the number of moles of gas number 2 times those same things. Again, R, T, and V are constant, so they stay the same. So the only thing that's variable is the number of moles of each of these gases. So P3, same thing. The number of moles of 3 times RT. So mathematically, you can factor out the RT. So the ratio of the moles of a specific gas in a container divided by the total moles of gas is called the mole fraction. Okay, we talked about that in the previous unit. So there it is, chi equals the number of moles of gas number 1 over the total number of moles. If we assume there's just 2 gases involved, then it's N1 plus N2. So since the partial pressure of a gas, P1, is proportional to its mole fraction, then what we can do is take the total pressure of the gases in the container, of all the gases in the container, multiply it. If we want to know the pressure just of gas number 1, we can multiply it by the mole fraction of gas number 1. It's N1 over N1 plus N2, and that gives you the pressure of just gas number 1. Of course, you could do the same thing for gas number 2 in this example. So example, a container holds 2 moles of O2 gas and 1 mole of H2 gas. What is the partial pressure of O2 gas if the total gas pressure is 960 torr? All right, so we figure out the mole fraction and we multiply it by 960. So let's go down and do that. So find the mole fraction of O2 and multiply by the total pressure. So there it is. There's the formula. So the total pressure is 760 torr. The moles of O2 is 2. The moles of H2 is 1, so you add those two together for the denominator. That's the total number of moles of all gases. So 2 over 2 plus 1 is 2 over 3. So 960 times 2/3 gives you 640 torr. So that's the pressure of just the oxygen. If you wanted the pressure of just the hydrogen, you would take 960 minus 640, and that would give you 320 torr for the pressure of the hydrogen. So kinetic molecular theory, this is just a general theory of gases. It's kind of similar to Dalton's laws, but deals with gases. So gases consist of large numbers of particles that are in continuous random motion. The combined volume of all gas particles is very small compared to the volume of the container. So think about what that means. It means they're almost never going to bump into each other. They're pretty much going to just fly around freely. Occasionally they'll bump into each other, but not very often. 3. The attractive and repulsive forces between gas particles do not exist. Remember, we call those Coulomb forces or Coulombic forces. It's the gas molecules, it's that molecules want to stick together. But in gas laws, we assume that they don't want to stick together. Remember what I said at the beginning of this unit? They're like little balls. They just kind of bounce around, bounce off of each other. When they do hit, bounce off the sides of the walls. But they don't stick together. They don't want to be attracted to each other. So this is the main characteristic of a gas. Gas particles are separate from one another. 4. Energy can be transferred between gas particles, but does not increase and decrease. So you can almost think about if you've ever played pool or seen anybody playing pool and you've seen two pool balls hit each other, they just kind of go click and they bounce away from each other. And so that's what we're assuming is happening. They're not spongy or soft and they're sticking together or, doing something where they're kind of losing energy. They're just bouncing off and going off in a different direction. And 5, the average kinetic energy, remember we call that temperature, of gas particles is proportional to the absolute temperature. This means that the temperature in Kelvin reflects the average kinetic energy. Okay, a couple of terms related to gases. So previously we mentioned Graham's law of effusion, which indicated the relative speed of two gas particles. So there it is, you're seeing it there again. We saw that in the first lesson. So the formula for the actual speed of gas particles. So remember, all Graham's law told us was that one gas molecule would be twice as fast as another. It didn't tell us exactly how fast it was going. Either one of them were going. But there is a formula for the actual speed in meters per second. So if you want to know actually how fast a gas molecule is moving, and it's this. And they use the strange letter little u there, and that's for the speed of gas particles. So it's 3 times the gas constant times the temperature in Kelvin over the molar mass. And so if you plug it in and take the square root of that, if you plug it into that formula, those variables, you'll get the actual speed in meters per second. So this is where u is the speed in meters per second. So the average speed of some common gas molecules ranges between about 300 and 3,000 meters per second. Okay, so keep in mind a football field is about 100 meters long. Okay, so there you have it, and that's at 25 degrees, which is about room temperature. So you can see oxygen is the heaviest of all those 5 molecules you're seeing down there. Oxygen is the heaviest, so it moves the slowest. Remember, it has a molar mass of 32. Nitrogen has a molar mass of about 28, so it's a little bit faster than oxygen. H2O, you know what that one is. It's 18.02, so it moves faster than oxygen or nitrogen. Helium has a molar mass of 4. Again, you get that right off the periodic table. And hydrogen is 1.01 times 2, just call it 2, so it's going to be faster. It's the lightest, and so it's going to be the fastest at a particular temperature. So air consists of N2 and O2 molecules, which have about the same mass, 32 for O2, 28 for N2. And therefore they have close to the same speed, not quite. So the graphs to the right shows the fraction of common gas molecules at various speeds. So diffusion is the random movement of gas particles in open space. So if you open a bottle of perfume in a warm room, it will spread. The perfume molecules will spread throughout the room. You'll be able to smell them everywhere. That's diffusion. Effusion is the movement of particles through a small hole. So effusion is a laboratory process that allows the speed of gas particles to be measured because it focuses them in a known space. So you have a known volume over on the right, and you have a hole of known size. So all the gas particles in that container on the right start off on the left-hand side. There's nothing on the right-hand side. And then it's just measured how fast, how long does it take them to equalize. Eventually you end up with equal numbers of particles on both sides, and how long does that take to happen. That's what effusion is. So mean free path is the average distance a gas particle must travel before colliding with another particle. Okay, so it's how far apart the gas particles are. That has to do with pressure, temperature, and some other things, number of moles and so forth. So ideal gas behavior, basically an ideal gas is one where the molecules don't interfere with each other. It's almost like a single gas particle out in outer space, and there's no other particles around to interfere with it. But ideal gas behavior does not perfectly exist in the real world. Ideal gas particles are not interfered with. They move freely. So gas behavior behaves most like ideal gases when the temperature is high. So this is because particles have enough kinetic energy to avoid being attracted to other particles. Think about when gas condenses down into water, into liquid water. Why does that happen? Because it loses energy. So if the temperature is lowered, causes the water molecules to want to stick together. So if the temperature is high, the gas particles are going to want to stay separated from each other. The other thing, so there you go right there. The other thing is if the pressure is low. This is because the particles are spaced far enough apart to avoid contacting one another. So, in other words, again, gases behave most ideally, that is, they don't interfere with each other when the temperature is high and the pressure is low. So van der Waals equation makes a correction for the fact that gases under high pressure and low volume, that means they're going to be squeezed together more, and low volume increases pressure, do not behave as ideal gases. So there's the equation. So you notice it takes PV equals nRT and it adds some things to it. So A is a factor that represents the strength of the attraction between the particles that makes a gas behave less ideally. So if the particles have a stronger attraction to each other, say they're polar molecules versus nonpolar molecules, then the A will increase and it will make the gas less ideal. The molecules will want to stick together and not behave as an ideal gas. B is a factor that reduces the volume. So you notice it's volume minus some number of moles times B. So that factor reduces the volume, and that ends up increasing the pressure and squeezing the molecules tighter together. So that makes them behave less ideally. So again, this is called van der Waals equation, and it's meant to kind of add something to PV equals nRT to deal with non-ideal gases. In summary, larger values for A or B mean that the gas behaves less like an ideal gas. And that takes care of our second and last lesson on gas laws. We'll talk about gas laws and add some knowledge to this as we go through the course, but that's it for this unit.